Hello, good evening, everyone. My name is Ahmed Ali, and I will be presenting alongside my colleague Jibin George. And today we will be discussing our project on the dynamic control of a microgrid using variable input with maximum power point tracking controlling algorithm through the P&O technique. And our project has been guided and supported and supervised by the Professor Ashraf Khan and the Professor Mohsen Jamil, whom we would like to thank for their support and directions. And let's dive now into the work. So we have two main questions over here in our project. The first question is why microgrid and why MPPT algorithm? The growing adoption of renewable energy sources is important step for combating the climate change. Microgrids are critical in this transition as they ensure the stability and reliability in the power distribution while integrating various renewable energy sources. The primary objective of our project is to investigate and validate advanced controlling strategies for a microgrid that incorporates both PV system and BESS, which is the battery energy storage system. In particular, we focus on employing the maximum power point tracking algorithm using the perturb and observe, the P&O technique, and also we will use a different type of a resynchronization technique to adjust to combine between our grid, which is the microgrid, and the main grid of the system. Let's dive into the system components. So our system comprises three main components, which is the PV array, the BSS, and the microgrid connection control. The P&O method is used for the maximum power point tracking, which is crucial for optimizing the power output from the PV panel, the PV array, sorry. Additionally, we utilize inverter control and load management techniques to ensure efficient energy storage in the BESS, the battery energy storage system. These methods collectively ensure that we extract the maximum possible power from the PV array while maintaining the efficiency of the system of the energy storage system. The design of our system includes solar array controller that implements MPPT to maximize the power output from the PV panels. This controller dynamically adjusts the operating point of the PV array to ensure that the maximum power point is extracted. Even under varying irradiance conditions, which we will see later, the BESS controlling system is another critical component for efficient system, especially when we have like varying irradiance conditions, which is responsible for ensuring the efficiency of the storage system, and it handles also the charging and discharging cycles, maintaining the battery within the optimal operating limits, and ensuring that the energy availability during the period of low solar generation. More insight view to our system design and the system components. Our system design includes the solar array controller, which implements MPPT to maximize output power. The BSS control system ensures efficient energy storage and management, of course. Additionally, our design includes strategies for maintaining a stable and synchronized connection between microgrid and the mini grid through resynchronization system. Um, the block diagram illustrates the primary components of the microgrid system, highlighting the integration of the PV array, BESS, and the mini grid. The PV array connects to an MPPT controller, as we can see, which optimizes the power output by adjusting the DC-DC converter through adjusting the duty cycle of the inverter of the switch, sorry. And this converter regulates the voltage from the PV array to match the requirements of our system. At the same time, the BESS is managed by a battery management system, BMS, and an inverter, a DC to AC inverter, ensuring efficient power conversion and storage. The BESS can charge or discharge based on the system's needs, controlled by the battery management system, as we mentioned before. And both the PV system and the BESS are feeding the grid tie controller that synchronizes and manages the power flow from the main grid and to the main grid, ensuring stable and reliable operation. And this comprehensive layout ensures seamless integration and optimal performance of the microgrid. So our system is we used one main application, which is the MATLAB Simulink, for our modeling and simulation. The key variable monitoring during the simulation includes voltage, current, output power, and state of charge of the battery. This setup allows us to accurately model the dynamic behavior of the microgrid under different varying conditions, for sure. Furthermore, our system incorporates strategies for maintaining a stable and synchronized connection between the microgrid and the main grid. This includes resynchronization units that manages phase, frequency, voltage alignment before connecting it to the main grid, for sure. Um, and after and by implementing these strategies, we ensure that the microgrid operates reliable and integrating to the main grid, enhancing overall stability and resilience. And my friend Jibin now will explain more about the simulation and the system.
So here we can see the simulation results for the solar plant. The graphs show us the irradiance, the boost duty cycle, the PV voltage, and the current. Our analysis, it clearly shows that the PV system remains stable and it is efficient even under varying irradiance conditions. This is mainly thanks to the MPPT implementation. For example, the irradiance level is stepped down from 900 watts per meter squared to 100 watts per meter squared and step back up. The boost converter's duty cycle adapts accordingly, changing from zero point 0.2 to zero point 0.8 to maintain. So if you look towards the left, you can see the basic battery and BESS control system. So you measure the SOC, the state of charge, the voltage, the current of the BESS. You check if the state of charge is below the lower threshold. If it is, you start charging. If it's above, and then you check if not, you check whether it's above the upper threshold. If it is, you start discharging, and then you adjust the inverter for the AC output, and then you keep repeating this process. So then on the right, you can see the simulation results. So these graphs are the result of our grid resynchronization system, as we like to call it. It shows the PCC voltage, the point-to-point coupling, uh, and the voltage, the frequency, the phase, and the power flow. Uh, our system clearly demonstrates efficient synchronization and power flow management between the microgrid and the main grid. Uh, for example, it's clearly seen that the PCC voltage remains stable at 600 volts and the frequency is consistent at 60 hertz, regardless of um, what radiance changes are there, whatever happens within the system. The phase difference adjustments are also minor, staying between plus or minus 5 degrees, uh, which makes it clear that there's successful synchronization effort. Uh, One of the most important things for a microgrid is its stability, or for any grid, as a matter of fact, is its stability. And one of the most important things, reasons that a microgrid needs stability is because it's often faced with rapidly changing situations, especially due to its power sources. This is controlled through the use of control algorithms, and in our case, the control algorithms that we designed were very robust enough to provide a stable power output. Um, the control algorithms provided their response to the changing irradiation of the values was both swift and stable, and also had minimal impact on overall grid stability. The BESS also efficiently mitigates the power fluctuations, ensuring a reliable power supply. So, our project successfully managed to create the control strategies for integrating the photovoltaic systems and the battery energy storage systems into a microgrid. These strategies significantly enhanced the microgrid reliability as well as its efficiency. The ability of the system that allows it to adapt to changes in irradiance and load demand while maintaining the grid conditions, stable grid conditions, shows that the implemented control strategies were a proper success. And for our future work, we are planning on exploring further advanced techniques such as ANFIS, which is Adaptive Neurofuzzy Interface Systems, and particle optimizations for optimization, particle swarm optimization for to improve the performance of the system further. This is another reason why this was very important, because we needed a proper test bed. We had to take our time to create this design. So, yeah, thank you for watching.